I couldn't find a good two proportion statistics joke, so I did find this nice statistics cartoon. And here's a normal distribution of statistics. These are those that exactly match reality. These are those that are mostly harmless, and these are the statistics that are dangerously misleading. So sometimes you're playing with fire when you're playing with statistics. All right. So let's go ahead and start comparing two proportions. How do we compare group A to group B in an experiment, or even if we go back and look at a survey or sample that was already obtained? Well, believe it or not, it's more common to compare two groups than to look at just one sample. It's more interesting. Well, if I'm going to compare two things, the best, usually I'm going to say, oh, one's higher or one's lower, but the easiest way to compare and just get a number is to take the difference, y minus x. Well, our new mean is just going to be the difference of the two proportions, the two percentages. So that's rather intuitive. And remember, when we have two different samples that we're looking at, and we take the standard deviation and the standard error, they're practically the same formula. That one should have a hat. Then when you look at it, you actually have to add you have to square the standard deviations and then add them, or square the standard errors and then add them. But it basically turns into this formula. Remember, it's like the Pythagorean theorem of standard deviation. Luckily, this formula is on your math chart that you will have access to when you take your AP test. So you don't have to memorize it, but you'll recognize it as PQ over N. In this case, since I'm trying to do standard error, and that should have a hat, we have the little hats on the P's to represent what we got from the sample. Assumptions and conditions are pretty much the same. We still need to randomization. We still need to hit the 10% condition. Now remember, this condition only applies if we're not doing replacement. It doesn't apply if you're flipping a coin or if you're doing something you can repeat infinitely, all right? It only applies when we're grabbing things out of the pool and not putting them back. There's also the independent groups assumption. The two groups should be independent of each other, all right? And the sample size, we still have the success-failure condition, but now we're checking for two groups. They'll need 10 successes and at least 10 failures to use a normal model. So our model is going to be normal, provided that they're independent and all those conditions are met. And our mean, like I said before, is P1 minus P2. All right, there I'm referring to the parameter. All right. Now, the null hypothesis, we're going to assume, and we'll do more of that in the next part, that this is equal to 0, that they're the same. So I will show you how to get null hypotheses from the examples, but we're not going to do much with it. What we will also be playing it more in the next part with standard deviation, which isn't much different from standard error. So the only difference is standard deviation is from the parameter, from the population, and standard error is from our sample. So we can create a confidence interval, because we're just going to look primarily at samples right now. The same way, the confidence interval is going to be our mean plus or minus our critical value times our standard error. And your critical value is going to depend upon what confidence level you want. Okay, and remember, for confidence intervals, this is always a two-tail. So if you want 95% confidence, that would be 1.96 standard deviations. Okay, standard error, and if you want to calculate the standard error, that's basically the same as what we've been calculating for standard deviation. And again, this is on your math chart. So let's look at our first example. We've got a support group who meets regularly to help people who are wearing the nicotine patch to help them quit smoking. So we're going to create a 95% confidence interval. Which one's better? One wore the patch and attended a weekly meeting, so we got group 1. And we have group 2 wore the patch but did not attend meetings. In group 1, 46 out of 153 successfully stopped smoking. In group 2, 30 out of 151 successfully stopped smoking. All right, if I was going to do a test, my null hypothesis would be that they're the same, all right, that this will be 0. And if I'm trying to show that one group was better than the other, I would say the difference of them is greater than 0, and I would put the higher proportion first. All right? So let's go ahead and start doing our confidence. Well, actually, before I can do a confidence interval, because I can always do my hypothesis before this next step, I need to determine if my normal model will work. Is this random? Well, the smokers were randomly assigned to groups. You didn't know this, but I did, but I didn't feel like filling the screen with all the text. All right, so they were randomly assigned. Success failure, group 1 had 46. Group 2 had 30, all right? And you can look, let's see, 46, there's definitely more than 10 left. 30, 151. I would go ahead and write down those values for failures as well. You want to make sure that the person grading your work knows that you know the number of successes and failures. Independence. It's pretty reasonable to assume they were independent, especially since they were randomly assigned. Okay, now to the math, the mechanics. So let's go ahead and calculate the proportion for group 1. That's just going to be 46 of 143. That's a typo. And that's supposed to be 143. No wonder I had 153 later. So that's 143 up there. My bad. And that's 0.322. Group 2 had 30 out of 151. It's 0.199. All right. When I take the difference, I find the difference is 0.123 or 12.3%. Okay. Now, I want to use a confidence level of 95%. So my Z critical value is 1.96. And I need my standard error, and I substitute in all these numbers, and I get 0.051. My margin of error, my plus or minus value, is just 1.96 times this 0.051, and I'm going to end up pretty much, actually I should have had a 2 on there, but I did it on my calculator and rounded. I got 0.100, or 0.023 to 0.223. So that is my confidence interval. And so what can I say from this? So it's basically this difference went in there. That times the Z value goes right there. Okay. And then to calculate these two numbers, I just go ahead and do the plus and I do the minus. Now, what's my conclusion? Well, I've got 2.3% to 22.3%. We are 95% confident that the support program could raise proportions of smokers who manage to quit by using the patch by between 2 and 22 percentage points. Now, one thing to keep in mind is, would legislators pay for this program? Well, some might be more tempted to look at the 2 percentage points and say it's not worth the risk. And then others might say, oh, look at the 22%, because we're giving a pretty huge range. Are there any ways that we could have made this even better? You know, because remember, when we're doing 2 groups, suddenly our standard deviation is getting bigger. Our standard error as well is getting bigger. And that creates a wider confidence interval. Well, obviously, one way to improve this is by sample size. Okay, our next example. In December 2002, Consumer Reports reported a study on the presence of bacteria in packages of chicken sold in supermarkets. We're going to go ahead and create a 90% confidence interval for the difference between Tyson and Perdue chicken for the presence of bacteria. So in Tyson, they found Campylobacter contamination in 56% of 75 packages. In Perdue, they found Campylobacter, I think I misspelled it, contamination in 33% of 75 packages. So if we did our hypothesis, if we were doing a t-test, not a t-test, I'm sorry, just a hypothesis test, we'd say that the difference should be nothing. And our alternate is that there is a difference between the packages. All right. So you can always start with your hypothesis, which we're not going to use in this part, but we'll revisit this problem. Okay, now the model. Can we use a normal model? Okay, random. There's actually no mention, but I presume Consumer Reports knows how to take a random sample. That's kind of what they do. Success, failure. Go ahead and calculate these out. You can see all my values are greater than 10, so we're good. Independence. Well, okay, you can put a check mark and let's go ahead and go with it, but they may not be mutually independent. Packages that are handled improperly might be more likely to be contaminated, and those packages may be delivered to the same store. So I'm not sure if they pulled all these packages from the same store or from different stores. But let's go ahead and proceed, since we've kind of covered our, we've hedged our bet there by saying, well, we're not sure about the independents, but we're going to keep going. All right. So let's go ahead and first calculate our new mean, which is the difference between the two. So it's like 23%. That's pretty high. Our critical value, because we want a 90% confidence interval, is 1.645. Our standard deviation is basically just putting these in the formula. 0.56, there it is, 0.44, 0.33, 0.67, 75, 75, 0.079. So my confidence interval is basically 0.23 plus or minus 0.130. All right. So my confidence interval is anywhere from 10% to 36%. So I'm 90% confident that the rate of Tyson package contamination is between 10 and 36 percentage points higher than the rate of Purdue package contamination. And this was done several years ago, so I think you're okay. I'm sure Tyson has done some improvement in that, or maybe it was just a bad sample. You never know.